We're going to review really well next Tuesday, but in the meantime, there is in the course content. There's this folder out here. No, I'm sorry, there's not this folder out here. Maybe there is. No, anyway, I'm going to put a folder out here in the course documentation for study material, and I'm going to make it. I'm going to set it up to where it goes active Sunday night. Cool.
All right.
Can we do?
Yeah,
Can we shoot for a Saturday?
Shoot for Saturday.
Saturday morning?
Like Saturday morning?
Oh, please say.
If so, I just lock myself in the library and knock them out.
Sorry. I already peeled this thing out.
You can do this material like your book.
Oh, yes, and on Blackboard, make sure you go through this logic and the graph set on this stuff. This cylinder graph set, PLC logic, go through that and make sure you understand how it works. Because you'll be designing a graph set on this test, and you won't. There's a little bit of PLC logic in it. Actually, you'll be doing the test and then a lab, an independent lab, but it's just going to be on timers. That's it. The independent lab. TON, TOL. Let me think of what else. I was going to put a test from last year out here, but here's the problem. We are too far behind. That stuff would not apply. It just none of it makes any sense right now for that test. Actually, we're not too far behind. We're behind about a week and a half.
Are we the only one behind?
No, every class is. Yeah. We got behind those, whatever it was, I don't know, 13 days, whatever it was, I don't know what it was. But somehow we got behind. Not a big deal. As long as you're learning, that's the main thing. What else? Timers. Make sure you know those timers really well. TON, TOF, RTO. That's a big part of it. And we'll do some practice labs today for the TOF timer. That will get you going pretty good. Anyway, we got to get rolling here because we need to review the timers. And then there's a practice lab. There's 4 practice labs that you'll be doing today, along with a handout. I know everybody's probably got the inside scoop on all this stuff already. No. You guys go hear from other classes?
Yeah, they would.
Surprise. Timers. Let's do some review so that everybody is 100% good with this stuff. And I want you to understand this stuff today. And please, when you go home today or over the weekend, please study this stuff. That's the only way you're going to get it. I mean, there's so many people that don't even pick up a book and read it. And they're always asking these obvious questions, you know what I mean? And it's not necessarily, I'm not saying anybody in this classroom, but it's in general. They're asking obvious questions that they should have known a week ago. You know, I'm like, read the darn book. It's pretty simple. Pick up the book once in a while, and you would know that stuff, right? I mean, it's not rocket science. On delay timers. What's the contact supposed to look like? What's it need to look like?
Like this.
Yeah, good. What types of contacts are these? What's the first one? Normally open,
Close.
time closed. Yes. How about the next one? Normally closed,
Time open.
time open, and the other one. Instantaneous. What'd you say? Instantaneous. Yeah, don't put instant on your test and you'll get it wrong. It's instantaneous.
Spelling it
I
wrong.
know there's a lot of it, I know it. I have to sound it out every time I spell it.
That's only if the power is made to that contact.
Yeah, as soon as the relay gets energized, it closes.
On your organization.
Now, with a normally open time close, which PLC instruction, or which timer bit will we use? Yes, the DN. About the normally closed, timed open. Timer timing. How about the instantaneous? Enable. Good. Now we're going to do the off delay. What kind of contact?
Normally closed time shift.
So it's normally open, timed open.
Normally open, time open. About that one.
Normally closed, time closed.
Normally closed, time closed. Does everybody get this?
Yeah.
I hope so, yeah. And this one, instantaneous.
That's instantaneously too?
Yeah, it is.
Okay.
Instantaneous.
Is that supposed to be timed open on the second one, or timed closed?
It's time closed. Normal close, time close, because it opens immediately, right? As soon as we energize, it opens immediately.
And then on time closed.
Yeah, time closed. Now, which timer bit do we use for each contact?
Was it used done for both of those? Or, yeah, for the first two?
Yeah. Yep. Normally open, timed open, we use the done bit. And here's the difference though. We use the done bit here also. But what kind of instruction do we use? XIO. Yeah. Yeah. And then instantaneous. That's the enable. This is the only one with the XIO. That's the, and that can be real confusing unless you, I mean, you gotta really think about it. If you're confused with these timer bits, come in this lab and work through it. That's the only way you're gonna get it. That would be my suggestion. Everybody's good? Okay. Something we haven't talked a lot about is timer applications. There are some real-world applications for timing. And we're going to talk about it. There are a few of them in the book, but book does not necessarily talk about real world stuff all the time, you're actually gonna see a lot of. Anyway. And we'll go through these one at a time. Cascading time. The enunciator. The dwell timer. The debounce. I was trying to, the other night I was.
Is this all chapter 7?
Yeah, it is. Dwell time debounce is not in there. Dwell and debounce are not in there. But it's not rocket science, so
We should know it in some.
Let me see. Yeah, and I was just thinking the other night, I was trying to brainstorm and try to think of some real world applications that are very, very common. We're going to go through each one of these, and hopefully you'll get it. These videos are on Blackboard if you need to look at them. The graph set video, it's like an hour and a half long. It's pretty good, so please review that video too.
You have that on Blackboard, you say?
Yeah, it's in the course content.
Okay, on the folder you said you're uploading
Yeah. Cascading timers. So when we cascade timers, and this is in the book, when we cascade timers, we set up a timer. And generally, what happens is this timer has reached its maximum value that it can time. So what we do is we add in another timer. See where this is going? So if that maximum number is 32,767, so if there's ever an application that needs to go higher than that, I don't know how many minutes or hours is that? I have no clue. If you divide it by 60. Yeah. Anybody have a calculator here?
So is it sequential reduction of time in a process?
Yeah, this will time out, the first one will time out, we get the done bit. And then it starts timing the next one. This is some input. Let's say we want machine time.
546.
546 minutes.
22. Oh.
Okay.
Nice.
Okay. So if we want to set up an 8-hour thing, we can figure that out. So yes, this one times out, first timer times out, we get the done bit, and then the second timer starts timing.
So if you have a 40 process or a heat treating process, you can time each process and, you know.
Mm-hmm, yep, yep. Exactly. Now, an application for something like this would be to set up like a clock or some kind of something that times the amount of machine time or some process. So what we would do, this would be set up for seconds, right? Seconds, 1 second. This one would be set up for minutes, 60 seconds. And the next one, what do you think the next one could be set up for? So we had seconds, minutes, hours, yeah, 3,600. Everybody kind of see what's going on there?
Should that be T42? You're going
This
T40?
would be T41 done. Yes, that way when this timer gets done, it starts timing the next time. Yeah. And we use this a lot when we get into counters. I usually wait until we're in counters to cover this stuff, when we're incrementing counters with timers. Real time.
So I might be jumping ahead here thinking, but so your output will only be controlled by your T42 timer?
Yep, that's right.
The other
Every
two
hour.
timers are only controlling the last one, and the last one control your output.
That's right. And generally what you do is we do something like this. T42 done. So it resets everything. Once we get the done bit from T42, it resets. Actually, this should be outside of here.
Mr.
That way it
Henry,
resets everything.
how is the D on the bottom different from the D in the middle there? You have D, right?
Yeah, this pen
Okay.
decided it didn't want to write. Actually, the board decided it didn't want to respond.
So with the different inputs like that, that means you're gonna have a different run on your input page for each one of those sequences?
Yeah, yep, that's right.
When you do your initialization, you're gonna have a callback for that, and then you're gonna have individual ladders on the input, and only one ladder referencing that process.
Yeah, yep. Something like this, though, it would all be in the same ladder. Some ladder, maybe you might call it a clock, or something like that. What we did was strictly examples, real world example inputs, outputs, main routine, false. And then you might have a subroutine called clock. Machine clock. Annunciator flasher, another one that's in the book. And I know everybody that's seen this. Down. Done. 1 second. 1 second. That should be 1 then. Kind of see what's going on there. So every second, these timers,
Constantly blink.
yeah, these timers are gonna go, they're gonna flip back and forth. Time, and so on, every second. So every second, this light's gonna flash. It's pretty common. If you have an alarm, let's say we have an alarm. What did I do there? Alarm input. We have input, then we start this flash, this enunciator. Like I said, that's in the book, you don't have to write all this stuff down. I wouldn't try to write it down. Well, that's true, yeah, that's very true, the more you write stuff down, you kind of puts it in your head.
Blue paint on the wall.
Dark blue or light blue?
Typically the light blue, which you think is sky, the space.
And then we're all over the place, like green,
That's the only thing I remember.
That's a collection of about 200 images that just scroll through. It's just stuff I've collected from all over Google. It's all concept art.
hang in there, bear with me, we'll get there. I don't want to just blast through this stuff because you won't get it. You know what I'm saying?
Why is it spread to the
So the well timer. So a well timer is normally set up, and this is strictly an example. Let's say that we're drilling parts. We're drilling holes in parts. We have this table, have a machine with a table. We have a part on this table. And we're going to drill a hole in this part. If we were to think of it this way, if we were to just take it and just drill it really fast, what's that going to do?
Too much torque, you're gonna strip the thread, break the bolt.
You can do a lot of stuff, couldn't you? Yeah. So what you do is you have a little bit of dwell time, you get down in the part, and you hold it there for just a second, right? You drill, and then pull the drill back out.
Maybe increase, cut down heat push.
There you go, WD-40. But, so that's to eliminate like burrs and that kind of stuff. If you add a little dwell time, it's going to help clean that hole out, right? As it drills through the part. You drill, it's just like you take a drill. You don't want to just go like that. You get burrs and all kinds of crap. It doesn't clean the hole out. So it's all about keeping the part cleaned out. Dwell time. And there's other applications that you guys can probably think of and have probably seen. Debounce. Real common application here, and I'll show you a couple of examples. Let's say we're filling a tank. We have a float switch. We're pumping water into this tank. That water is not going to just slowly and nicely and smoothly ride up into the tank, right? It's going to be doing all kinds of agitation and all this stuff, right, as it's filling. So once we get to the full level, this float switch, what's that float switch going to be doing? Bounce on and on, that's right. Float switch is going to be bouncing on and off. Meaning the pump's going to be bouncing on and off, right? Meaning you're probably going to trip out overloads or do something to the pump. So we add some debounce time in to smooth that out. And I know you guys have seen this stuff before. You didn't know, maybe. Let's write some logic up here to give you an idea how it works.
Basically, lake versus island.
Yes, that's exactly right. And there's two ways you can do this. The most common that I've always used in the real world, use a TOF timer. We have this input. Some switch, some physical input that's measuring something, or just to know that there's a part present, or we have a tank full. And then at this point, we use the done bit from the TOF timer to actually say that that switch is good to go. See what can happen there? So as soon as the switch is made, but let's set this up. I'm gonna set for something really crazy, 5 seconds. That's a lot for debounce. You see what's gonna happen? As soon as we energize the timer instruction, we get the done bit, right? We energize, we're bouncing, the water's bouncing all over the place. We're still filming. But the timer got energized, we have the done bit. Now that water can still bounce, and it can bounce for 5 seconds off of that switch, right? And still be okay. See what I'm saying? Because this is gonna time out, it's gonna take 5 seconds for this done bit to go false.
So basically, if you have a utility system for an apartment or something, you're using this so that you'll get crazy readings on the meters all the time.
I don't know. Can't think of how that would work or what. I don't know. This is more for like a switch that's gonna bounce. Another application would be, let's say we have parts running down this conveyor, right? And at the end of this conveyor, we have a stop, some kind of a steel bar that's energized with a solenoid that moves up into the conveyor to stop these parts. Let's say we have some heavy parts, heavy steel parts running down this conveyor. And we have a switch here, some kind of a switch mounted here. With the conveyor running, isn't that part gonna, once it gets down to the end, is it gonna bounce a little bit? It's a big steel part running down a conveyor. You think it's gonna have some kind of inertia where it's gonna bounce a little bit once it gets down to the end of this thing? Yeah, probably. We might not see it, but it's gonna happen so quick, it's gonna bounce a little bit once it gets down to the end of the conveyor. So what we do, we put some D-bounce on that switch. That makes sense? That way we can be, that switch doesn't have to be made for 5 seconds in this example and still be good to go. Another, and probably a better way to do this, I never used it. I always used just the timer off. Is the first timer you set up is a TON with that input. And then you set up another timer with that same input that is a TOF. And then off the TON, we have a bit level instruction, a binary. Then we take that binary and use it again in this kind of seal-in logic. See what's happening there? It's kind of hard to understand. A lot of people don't understand it. The TON instruction, what it's doing is once that input's made, that input has to be made, right? It has to be made for 5 seconds. That means we know for darn sure that it is 100% made, right? It's solidly made. Make sense? So we give it a little bit of time. Once we get the done bit from that TON timer, we know that that input is solidly made, right? I mean, there's no doubt about it, it is made. And then the TOF sets up the same scenario where it can be not made for 5 seconds. So we know that the switch got solidly made. We don't have to worry about that bouncing thing. And then we can be, it can come off the switch.
So in the, if you did the Boolean equation of this, you would have 2 variables that are the same in 2 sections of the equation for B3, 0,
Yeah, it used to be A, or B, and C. Right? Yeah. D-bounce time. Machine on dwell, what do you think that does? We're just gonna talk about it, I'm not gonna.
You press the button and hold it down for 5 seconds.
Yes, perfect. Everybody understand that? Machine on delay. So it makes it required where you have to hold in on that button for a couple seconds, rather than just, because it's real easy to just walk up and bump it. You don't want an operator that's bumping the button and turning the machine on, or anybody else. For that. Self-resetting, self-run timer. You see this a lot when we're implementing counters. Pretty simple concept. And we have some input. You see what's going on there? So it's resetting itself. It's simplified things. So every 5 seconds, it's going to time out and make the done bit, make this instruction go false. That's going to reset the time. Every 5 seconds, the done bit, XIO instruction goes false, time surprises. See what I'm saying? And generally what we do with this is we increment counters. CPU, take the done bit, although we haven't talked about counters yet. But we're incrementing this counter every 5 seconds. Incrementing the counter every 5 seconds. So we can set up a minute counter, an hour counter, a day counter, and so on.
Basically make a bot.
You got it. It's all. Yep.
Like using that logic, you could just make a
Oh,
bot.
there's
Seconds counts minutes.
next to open and close.
Loop to each day. Pretty sure that's what it's just.
Or was that supposed to be?
Just set the microphone.
Yeah, so this would be,
That's exactly what this is doing. Right?
this would just be an input.
This one.
And that's, with resets the timer, self-reset.
That's how phones are too.
Couple other things we need to talk about, and then we're gonna take a break.
It's so simple.
And then do some practice.
Now that you know what it is, otherwise you just don't know.
Whoa, how's that?
Implementing that time.
And we're not even talking about how digitally stacked together. The screen was like a nightmare.
Counter to reset. So you don't have a reset.
God, I feel like I just punch myself.
So if it's intended, what's the point of doing it?
Actually, this would be set up for seconds. 1 second, or every second, we'll set this up so it makes it a lot easier to implement using this type of logic and this timing. We'll get into that. Or
Are you like
MCR fence zones, something we need to talk about a little bit more. Everybody recall this stuff? MCR fence zone. So here's a fence zone, and what do we put inside this zone? Yeah, exactly right. It's always outputs in it. Oh, 0, 0. Oh, 0, 1, and so on. Yeah. Do you remember how it works?
Is that where only the inputs go and those road? I mean, the actions or something.
When it's done with all its outputs.
Yeah, so here's what happens. This first rung has to stay true for these outputs to even be scanned and energized, right? If, here's the key, if one of the outputs inside this zone or any of the outputs are energized, let's say they energize, and then the MCR, this first MCR instruction goes false, it's going to de-energize those outputs. Good? It's just like an MCR on a machine, right? The relay logic. Did we talk about that a little bit? Remember, MCR, master control relay. Remember what's going on there?
Yeah.
Okay. Yeah. Yeah. So as soon as that relay drops out, it's going to open the contact and shut off all the control voltage from the contact down. Same principle. Same thing. Except it's called master control reset. I don't know why Al Brown decided they would name it that. Group of engineers again. Would be my guess. Now, here's something. Let me do this. I'm going to make one of these a latch instruction.
Shouldn't both of those be XIC?
This is just some kind of conditional logic for that first run. Yeah, it can be anything. I'm going to latch one of these outputs. First of all, you never want to latch real-world outputs, right? So it wouldn't make sense anyway. But if we had something like this, V301, and generally you're not going to put binaries inside this fenced zone, but what's going to happen, let's say we latch up, and then the first MCR instruction goes false. Is it going to stay latched up?
Yes.
Oh, unless there's something.
Exactly right. It's any retentive instructions, we don't want to do that. Same with like an RTO, it's a retentive instruction, counter to retentive, so no retentive instructions inside that. It's that inside that. And I think we better take a break. Once you guys recovered a little bit. Yeah, that's right.
When you say it's because you have the MCR and college lines, if there were anything else at the bottom of that, it would not be
Well, that's a retentive instruction, actually. Yes, we would. Will you? What it cost you?
No, it's good. I'll just tell them.
So the first one is 7-9. And let's look on page 56 because the diagram for that is on the top of page 56. Is everybody on page 56? All right. So we have 3 TOF tires, right? Look at the diagram. When the switch is made, what's the motor's gonna do? Those motor outputs. When the switch is made, they're gonna turn on immediately, right? Because we're using done bits. And then when the switch goes false, you see what's going on?
Yeah, they're gonna stop 5 seconds apart.
That's right. They're gonna shut down in a sequence, right? And that is pretty real world stuff, right? Because when you shut a machine down, you don't wanna just go, you know, shut the power down, boom, it's done. Like a large assembly line, you don't wanna do that either. You shut it down in stages. You know how it is, like at the end of the day, end of the shift, you shut this thing down in stages. You don't wanna just shut everything down all at once and hammer down. So, yeah, they're shutting down in stages. A good example of that would be like a wash, kind of a parts washer, where you have maybe a pre-rinse, a wash, and a post-rinse. There you go. So if you
Motors will
have,
come on immediately. All the motors will come on immediately, they'll shut down sequentially.
yes, yeah. The next one.
Do we need these overloads in there?
No, disregard the overload. 7-10. There's no real world application for it. I don't have a clue of what it's even for. If you can figure it out, then I'll give you a thumbs up. 7-11. So look at 7-11 real closely. Look at the tanks. There's 2 tanks, there's a pump, and there's 3 pressure switches on that pump, right? You have tank A, which is being pumped into tank B. What the logic does, the first line of the logic, to start up the pump, you see the conditions to start up the pump? The main one there is PS1, right? That pressure switch. So we want to see inlet pressure on the inlet of that pump before we start it up. Why would we want to do that?
So that the pump won't pump or dry.
Won't burn out.
What's that, John? Jonathan?
Chris.
6 o'clock. Sorry, Chris.
Well, I was thinking it was, I was thinking if you were pumps, so you would need the forward pressure of the water to actually toast the pump.
Well, you don't want to run that pump dry, right? It's just going to make it go to toast. It's going to destroy it. Yeah. And then pressure switch. So we start up the pump, and you see the 5-second timer there. So what happens if we don't make the other 2 pressure switches within that 5 seconds? It's going to shut the pump down. That's what the T4-5 done bit is doing. See how that's working? It's a safety. So both of those switches both the pressure switches have to be made, or it's going to shut the pump down. Yeah, I don't know. They really don't. They're not really showing any devals in here, but they should. 7-13. So we have this motor, and we have an oil pump. See the pump output? That's for oil. What we're doing, T41, you see it's being energized immediately.
Which one is this?
7-13.
Yeah, it's on the top of page 59. So the pump, it turns on immediately, right? Because we're using the TOF instruction. Pump turns on immediately, and then 10 seconds later, the motor turns on. we shut the motor down, and the pump continues to run for another 15 seconds. So we're lubricating some bearings or something on this thing. RTO instruction, what do you think it's doing? Take a real close look at it.
Once it reaches the preset value, it's gonna,
Cut back on.
it's gonna turn the pilot light on to say you need to maintenance on it or something.
Yeah, it's also,
So, shut off after that 10,800 seconds.
yeah,
Well, yeah, and then they turn the pilot light on.
yeah,
To track the total running time of the pump.
there you go. What'd you say, Aaron?
A retentive timer is used to track the total running time of the pump.
Okay, does it tell you that? That's exactly what it's doing, yeah. So the pump, you see the pump input to that RTO, the retentive timer? The pump input can go true for a while, then goes back false, but it retains the accumulated
Yeah.
time, right?
What do you want us to actually set that at? Because we'll never see it running for
Right.
10,000 in, what, like 30 seconds or something? Or
That's probably
a
good.
minute, 60 seconds?
Yeah, 30 seconds. 35. Yeah, so it's keeping up with the total run time of the pump. Anyway, so
And
you're
then
off.
when that reaches, we turn the pilot light on, then we should get formatted.
That's right, yeah,
Change the oil.
yes, yep, yeah.
Yeah, whatever.
Yep, that's right, that's right. And then, just work through them, you'll have plenty of time if you work through them, but I want you to understand how they actually work.